All right, folks, welcome back. Here we go. Physics again. Fun times for us, right? Hey, hope you had a great break. Hope you got recharged. Hope you got enough sleep. If you didn't, then sorry about that. If you worked too many hours, sorry about that as well. Okay. So we start a new chapter today. This is going to be called Unit 6 Work, Power, and Energy for us. All right. So when we look at this chapter, what we're going to see is here's the layout for you. I'll make sure that this goes on Schoology for you as well. You can see Monday, Tuesday, Wednesday are typically note days for us. Thursday, Friday are quiz or test days for us. All right. Also notice that on Monday and Tuesdays, we're going to be 30 minutes in. So that's 10:30, that's 11:40, that's 1:15, right? On Thursday, Friday, we're going to meet right at the start, 10, 11, 12:55, if that for you, okay? That allows you then to get out, do those quizzes, do those tests, get that stuff taken care of within that class hour or that designated time, all right? So today what we're going to do is we're going to talk about energy work, work on an angle, and then I'm going to turn you loose and let you run some practice stuff, all right? So work and energy are measured in joules. Again, this is a metric unit for us. For us, we're going to measure energy in calories. Now, food calories versus regular calories, there are a difference, but don't worry about that. Think of it like when you ingest food, those are our food calories. All right, when we're burning energy off, that's food calories as well. Okay, so mechanical energy. Now, with mechanical energy, we want to know what might this be? Well, for us, mechanical energy involves energy that is moving things. So if your body fires its muscles, that's mechanical energy to get to move, right? If you go over the top of a hill on your sled or skis or snowboard and go down, that's mechanical energy. If you press the go faster button on your car, that's mechanical energy, right? Other types of energy: electrical, thermal, electromagnetic, nuclear, and that's just a couple. I mean, we could have chemical, we could have anything like that, right? Electrical could be as simple as connecting a battery to a circuit, right? Finding a break in the wires, putting them together, like you see when you're going to jumpstart a car. You put the two leads close together, you get that little bit of electricity, right? Thermal could be a fire, like a nice warm fire in your fireplace or a bonfire. It could be that steaming cup of hot coffee that is radiating. Electromagnetic comes from the sun for us, really nice. Nuclear, like fission versus fusion, okay? And those are just a couple that we can have. For us, we're going to deal with mechanical because movement for us is what's important. That's kind of the continuation of what we've talked about up to this point. So mechanical energy becomes important in this chapter for us, all right? So what you can see is a skier skiing downhill. That's mechanical energy because they're moving, right? You could see a bicyclist, right, using their legs or the hill to move. Okay, we can see this plane here. I'm trying to look. Yep, that's a prop engine plane. So it's using gasoline to turn cylinders. Cylinders then turn those fan blades or those propellers and allow that thing to move, right? Drift car, getting a little angular movement, right? So we're trying to move that thing in a circle, all right? And then last one, kind of funny. See a bear run down the road. Well, guess what? Now you're going to turn into mechanical energy because you're going to run like heck to get the heck away from that, especially that bear. Whew, that sucker big. All right. Now, energy. Richard Feynman is a Nobel Prize winner, and he's kind of one of these people who has talked about energy pretty extensively. And he has a really good take on it. And I know you're looking at this and saying, seriously, from 1961? It still applies here, and I'll twist it a little bit at the end, okay? So basically what he said is this. There's a factor, if you wish, a law, governing all natural phenomena that are known to date, all right? There is no known exception to this law. It is exact so far as we know. The law is called the conservation of energy. Now, you've heard of the conservation of stuff before, conservation of mass, right? When you're balancing equations in count. So you had to have the same number of atoms on one side as you did on the other side, same number of grams on one side as you did on the other side, right? We've talked about the conservation of momentum, right? Vehicle crashes, boom, all that momentum has to be transferred somewhere else, okay? So it basically states that there's a certain quantity, which we will call energy, that does not change in manifold changes which nature undergoes. What that means is that the amount of energy that we have doesn't change. So once in nature, it starts to move or it starts to change its location or its purpose, then it still stays the same throughout, the quantity, I should say. This is the most abstract idea because it is a mathematical principle. It says that there is a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It is just a strange fact that we can calculate some number, and when we finish watching nature go through her tricks and calculate the number again, it is the same. Basically, what we mean is that we can go through and figure out, we go for a run. We can figure out how much energy we burned. Well, what we can see is the amount of energy we exerted is the same amount that we put out into the environment. Okay? So it is important to realize that in physics today, we have no knowledge of what energy is. Now, I looked this up because I'm like, okay, 1965, just like you said, or 1961, just like you said. And to see, like, we have to have made steps. But guess what? We haven't. All right? A simple description for us is this. Energy is that which is required to do work. Now, the analogy that they've made today is a super simplified. They talk about children's blocks. That's why I had them on the front. So say that you have 10 children's blocks, right? So at the beginning of the day, you play with them, okay? And then your mom goes to put them away at night, right? Well, she sees 9 blocks out and finds 1 underneath the couch. So there's always 10 blocks. Next day, finds blocks out, 3 blocks under the couch, 2 blocks out underneath, another piece of furniture. Okay. Next day, 10 blocks are there. All of a sudden she counts, hey, you got 12 blocks. Where these extra 2 came from? Friend came over, right? Then next day, 10 blocks. She counts them at night. She sees 8 blocks, but inside of this object that she can't open, she finds that the mass, the weight, the amount of energy in there is worth 2 blocks. So this is what they talk about, is that, yes, we know that there's this total amount of energy, and it doesn't change, meaning that it doesn't increase, it doesn't decrease, it just gets transformed into something different. So even though we don't know necessarily what energy is, right, because of all those different forms, we can still see it at work, okay? So if we look at this, all right, now I know this is a state of hockey. What we're seeing is this hockey skater is putting energy into his hockey stick. We can see that, right? Because that thing is flexing. That stick is not made to look that way, all right? Even me as a person who played hockey until 2nd grade, right? Big time. I know I should be in the NHL right now if my parents hadn't decided to put me into basketball. Damn, I missed my opportunity, right? But you can see he's putting a ton of energy in here, right? As soon as he hits the ice, what happens is that energy is going to get transferred to that puck, right? And that puck is going to go, right? So when we see this concept of work is that force times a distance, all right? So work is force exerted over a distance because that energy he's putting into it is a force, right? And we shoot that puck. The more force he puts into it, guess what happens? The farther it goes, the more work we have to do, all right? Our force is measured in newtons. Our distance is measured in meters. Our work is in Newton meter or joules, all right? Now, again, if you look here, you can see, let me get this little dealio here, right? Newtons, meters. Newtons times meters gives us a Newton meter, all right? Now, I'm not going to go all college physics on you and show you how to derive the term joules from Newton meters because we don't care, okay? But both of those are going to work for us. All right. How much work is done against friction, sliding a box across the floor, delta D of 10 meters, if the force of friction is negative 100 newtons? And V is constant, all right? Here again, velocity constant, we don't have an unbalanced force, all right? We don't have acceleration, so that allows us to say that our applied force is our friction, right? So work equals force times distance. Well, when we look back up here, we're going to see this is important and this is important, right? Because that's a distance and that's a force. So what we're seeing here is our work is going to be the work against the kinetic friction, right? Meaning that this is that applied force. It's going to slide eventually, okay? So what we see is we've got 100 newtons. You can make it a negative 100. I'm okay with it, right? So the work done by the person is that force opposite of this force of friction, right? So the work done by the person is 1,000 newton meters or 1,000 joules, because the force of friction, if it's not accelerating, we have balanced forces, right? The backward for the friction is the same as the forward going forward. So we get 1,000 joules. Work done by friction should just be a negative 1,000, right? So once we see that, that becomes a way that we can calculate work. All right. So now here's the crazy thing. We don't need time, acceleration, or velocity to calculate work. So what we can talk about is that if we're shooting that puck across the ice, we don't have to talk about how fast, how much acceleration it does, how much time it takes. If we want to shoot that puck the length of the ice, we can either do it really slow and try and accelerate, or we can do it really fast, right? It's just a force times the distance. It doesn't matter how quick we go. Think of pushing or moving a desk, right? We slide that desk. It doesn't matter if we do it really fast or if we do it really slow. The end result is the end result. We just get it across the room, okay? So it's just how hard you pushed or how far you pushed or how hard you pulled. That's all we care about for work, all right? So let's try these out. How much force does it take to slide a 1,000 Newton crate across a floor at a constant velocity if the coefficient of kinetic friction between the crate and the floor is this? All right, so we want to know how much force does that take? All right, part B, how much work is done if we slide this far? Now, check this out. In this first one here, right, we've got a force and we've got a coefficient of kinetic friction. All right, so this force here to take a 1,000 Newton crate. So if it's this force is in this place, remember this here is our normal force. Mu, that's our coefficient of friction. So what we're going to see is, in order to find our force of friction here, we're going to take mu times our normal force, right? Because that's right in front of the word crate, that tells us that that is its weight, all right? So once we know that, our force of friction is 105.0 newtons. Okay? For us now, how far do we slide it? We want to find work. So if we know that we have to apply 105 newtons of force just to get this thing to move, well, how far did we make that thing slide? Well, we slid it 3.14 meters. So what we end up seeing is our work here is 330-ish joules, or 330 Newton meters. All right? Now, what happens if this force is applied on an angle? Because we don't always get it perfect. We don't always get that side pull to it or that side push. So if we apply this thing on an angle, right, what happens is that we see our force is still going to be directed straight through that handle, right? Now, as far as we're concerned, the direction of motion is the most important thing. We are actually wasting energy going up at an angle, all right? The reason we're wasting energy is because some of that force leaks out vertically. We don't care about that vertical part. We care about the horizontal part because that's the way that we want to get this thing moving. All right. So in order to look at this, check out the change. Well, if I only care about this direction of the blue arrow, right, if that's my angle, right, you can see here, this is going to form a nice 90-degree angle. This is my hypotenuse. Right? If this is the angle I care about, this is my opposite side, right? Up. This is my adjacent side. So when we look at this, for our purposes, that's where the cosine comes in. So that's the cosine, right? Because it's adjacent over hypotenuse, ka. So we're going to use cosine of theta here. Will it always be cosine of theta for this one? Yes. Especially if we want that horizontal force. Do we ever care about the lifting force? Not if we're trying to move it sideways, all right? So understand that that becomes a new different formula for us. So make sure, circle star highlight that thing as well, okay? So A human drags a cart by the handle a distance of 775 meters on level ground. The human pulls on the handle with a force of 75 newtons. The handle makes an angle of 35.0 WRT. What does that mean? With respect to the ground. So that tells us that this angle right here is 35, right? This force here is 75 newtons. Sorry, I forgot my degrees, right? So how much work does the human do? Well, we need a force, we need a distance. So what we see is, all right, if we know this is a force, we know this is a 35-degree angle, you can see you can preload and just do this all together. Make that F. So you can take this 75, plug it in here. You can take the angle, plug it in there. So take your 35 right there, right? You can take your 75 right there. And you can plug those two in and preload them like I did for this side over here to find my horizontal component of that force, right? Or you can just do it all together, which is probably what I'll do at home. Okay, so there's my force. There's my angle that we're running this thing at, and that's the distance this thing traveled. It should be 47,613 Newton meters, or 47,613 joules. Okay? Either one of those two answers is absolutely perfect. All right, so here's the formulas that you need to have down now as well. All right, so work equals force times the change in distance. Work equals our force cosine of theta times our change in distance. Now, also, don't forget this force of friction here. Oops, sorry, that got bad. Oh my Lord, that's terrible. Could equal force times our normal force. All right. Those are the formulas you want to have circle start highlighted or in a bank somewhere so that you can start to see stuff and work through stuff, right? We are going to add to these as we go. All right. So now go ahead, get out, try practice one. I'll put a walkthrough with it so that you can see what this looks like by about midday at the latest. All right. So get out there, try it out. Let me know if you got questions or anything like that. Otherwise, welcome back. It's good to have you back, and take care. All right. See ya.